Assalamualaikum and salam sejahtera, everyone. Good morning. Hope you all can hear my voice clearly. So perhaps we can wait for another 5 minutes until 9:05 a.m. before we start this course. So we let the rest to join our session first, if it is okay. Thank you. Okay, I think we can start now. So, Assalamualaikum and good morning, everyone. Thank you very much for joining this session. So before I start, can you all hear my voice? Perhaps you can give me a thumbs up, so at least
Very,
I.
very clear, Professor. Very
SAIZAL.
clear.
All right, thank you very much for the feedback. You can also give me a thumbs up. Yeah, thank you for that. Okay, so yeah, so welcome to another session of uh, a research methodology course, and this is for first year student, yeah, that enrolled in the university. And yeah, again, thank you very much for joining the session. I am SAIZAL PINJAMAN, and today I will give or conduct this session where we will discuss about the diagnostic task for secondary data. Yeah, and yeah, we will try to make this session as casual as possible. Yeah, and if you have any question, you can simply switch on your microphone, or you can also put your question in the chat box. Is it okay? All right. Okay, so due to the slow internet connection in my place at the moment, I have to switch off my camera. Yeah, I usually during class I used to switch on my camera, but at this very moment I have to switch it off. Yeah, because of this internet connection issue. So apologize for that. Yeah. Okay, now let me share my screen. Okay, I hope you all can see the screen. So as I said before, this is uh, another session of a series of research methodology course for first year postgraduate student in the faculty. And in today's session, we will discuss some of the diagnostic tasks for secondary data. And of course, when we talked about diagnostic tests for secondary data, there are various tests that involve, but due to time constraint, we will be focusing on a couple of diagnostic tests that are very important for secondary quantitative data. In this session, we are going to focus into the autocorrelation as well as the multicollinearity tests. So basically, diagnostic test, if I can explain about what diagnostic test is. So basically, diagnostic test is the last process, if you can call it a process, of quantitative data analysis. So in quantitative secondary data analysis, we have a pre-test, and then after that, we have the uh, regression analysis. So regression analysis is, I believe, the most common method of analysis for secondary quantitative data. And after the regression analysis, then we then move to the diagnostic tests. So the diagnostic test is used to identify whether the analysis that we have conducted follows the assumptions of the analysis, or follows the assumption for the regression analysis itself. So what is regression analysis? Of course, we are not going to explain about what regression analysis is, because that is not the focus of our workshop today. So, but basically, regression analysis uh, is an analysis that is used to identify the relationship between the variables of interest, to identify whether the independent or explanatory variables are significant in explaining the dependent variable or not. So that is a regression analysis. And after the regression analysis, then we have to conduct the diagnostic test. So that diagnostic test is used to identify whether the regression analysis that we have conducted followed the assumption of the regression analysis or not. So as I said before this, yeah, there are various tests that we can use to identify whether we can accept the results that we have obtained from the regression analysis. And in this case, we're going to discuss on the two most common diagnostic tests for regression analysis, namely the autocorrelation test, as well as the multi-correlation and test. And of course, in this test, our focus of discussion will be towards the secondary data quantitative analysis rather than the secondary data qualitative analysis. All right, so we will move to the first part of the workshop, which is to discuss about the diagnostic tests of autocorrelation, where we will try to answer these following questions. First, we will try to identify the nature of autocorrelation. So we will try to discuss what is autocorrelation. So when we read various journals, especially those that are dealing with regression analysis for quantitative data, we will frequently see this term autocorrelation. So what does it mean by autocorrelation? So that is the first thing that we are going to discuss in this workshop. And then after that, we will also try to identify the theoretical as well as the practical consequences of autocorrelation. We will try to see what is the what we call as effect if our estimation contain autocorrelation, both theoretically as well as practically. And then after that, we will try to see on how do we detect this autocorrelation. So there are various methods you can use to detect autocorrelation. So most commonly we use the Durbin-Watson test, but apart from that, there are also various methods we can also use to detect the autocorrelation. And then of course, after that, we will try to see the what we call as some of the remedies to what we call as to minimize the problem of uh, autocorrelation. So the nature of autocorrelation, as you can see on the slide, basically autocorrelation can be defined as the correlation between members of observation ordered in time or space. Yeah. But when we talked about autocorrelation is usually associated with time series data. So when we are using a time series data, we basically are dealing with autocorrelation, or there is a risk that our time series data contain autocorrelation. But even though that autocorrelation is usually associated with time series data, but autocorrelation is also present in the cross-sectional data. So in this case, we usually call it as the spatial correlation. Yes, spatial correlation refers to the autocorrelation in space, or it refers to the problems of autocorrelation in the cross-sectional data. So data can usually be divided into three. First is the time series. Second is the cross-sectional. And then the third one is the panel data. I'm not going to explain each of these types of secondary data. So, but basically there are three types of data for secondary data. First is the time series, second is the cross-sectional data, and then the third one is the panel uh, data. So autocorrelation is usually associated or present in the time series. However, it can also present in the cross-sectional data, which we call as the spatial correlation. So simply, autocorrelation means that the expected value of the product of two different error terms, ui and uj, is 0. So in this workshop, we are going to use some of the technical terms. Yeah. So I hope that you can understand what are these terms. And I'm not going to explain much of these technical terms due to time constraints, but you can check on these terms later on. Yeah. So yeah, symbolically, no autocorrelation means that the expected value of the product of two different error terms, ui and uj, is 0. So here we have the error term of a particular time, ui, and the product of the expected value of the product of the error term at ui and uj is equal to 0. Yeah, it is equal to 0. And that means there is no autocorrelation in our model. So here I is not equal to j. That means that we are identifying the expected value of the product of two different error term, ui and uj. So in the econometrics, we usually refer the error terms or denote the error term with the symbol u or mu sometimes. So the disturbance term relating to any observation is not related to or influenced by the disturbance term relating to any other observation. So what does it mean by the expected value of the product of two different error terms is equal to 0? So that means the disturbance term or the error term relating to any observation is, for example, the error term at ui is not related to or influenced by the disturbance term relating to any other observation, for example, uj. So the error term at time j, for example, is not influenced by the error term at time I or at the error term of observation I. So say there is a labor force or labor strike affecting output in one quarter, there is no reason to believe that disruption will be carried over to the next quarter. So that is what no autocorrelation means. So conversely, what does autocorrelation means? So this is as indicated in the equation 10.2, where here we have the expected value of the product of two different error terms, error term at I and error terms at J, is not equal to 0. Yeah, the expected value of the product of two different terms, UI and UJ, is not equal to 0. It means they are equal to something other than 0. It can be negative and it can also be positive. So in this case, the disturbance term at UI is related to or influenced by the disturbance term to any other observation, for example, at UJ. So I and J here refers to the observation either in time series or the observation at different cross-sectional values of our data set. So talking about the autocorrelation, if we graphically present the autocorrelation, we may be able to get the patterns as indicated in figure 10.1 here. So here we have figure 10.1a, b, c, and d, which represent data that contains autocorrelation. And when we talked about autocorrelation, the autocorrelation can be linear as indicated in figure 10.1b and 10.1c. So linear means there is a direct correlation between the disturbance term. So we can get figure 10.1 as you can see on this slide by plotting the error term or the disturbance terms against time in our data set. And of course, apart from having an autocorrelation that is linear, the autocorrelation can also be nonlinear as indicated in figure 10.1a and figure 10.1b. So it means that the relationship between the disturbance term, remember when we talked about autocorrelation, it means that there is a relationship of the disturbance term or the error term at different observation. That observation can be in the form of time or cross-sectional data or cross-sectional information or observation. So apart from a linear relationship between the disturbance term, there are also some relationships that are non-linear, which can be in cubic or in quadratic, as indicated in figure 10.1a and 10.1b. In figure 10.1e, here we can see that there is no apparent relationship between the disturbance term when we plot them against time. So here we can see that these disturbance term are random. Random means that there is no apparent trend that we can see when we plot the error term against time. Okay, so what are the factors that contributes to autocorrelation? Well, technically, there are several factors that can lead to autocorrelation. Yeah, there are several factors that contributes to autocorrelation. First is the inertia or sluggishness. Remember, at this session, when we talked about autocorrelation, we are going to focus into the time series data rather than cross-sectional data. Even though we can also associate the autocorrelation with cross-sectional data, but since autocorrelation is usually present in time series data due to the nature of autocorrelation itself, our focus of discussion will be towards the time series data. Yeah. So the first factor that can contribute to autocorrelation is the inertia or sluggishness. So as you can see there on the slide, sluggishness refers to a momentum built into this time series, and the upswing continues until something happens to slow them down. So this is usually present uh, for time series data, where a momentum that built into the time series and the upswing continues until something happens to slow them down. For example, there you can see when economic recovery starts, most of these time series start moving upward. They will keep on moving upward. Yeah. And this upswing, the value of a series at one point in time is greater than its previous value. For example, yeah, say for example that we are recovered from COVID-19 pandemic. Perhaps our economy will recover as well, and this will lead to an increase uh, in the income, for example, and that is the upswing. So it means that the value of our income will keep on increasing time after time. So this may also lead to autocorrelation. Another factor that can lead to the problem of autocorrelation is the model specification error. Yeah, model specification error. So when we analyze the relationship between explanatory variable with the dependent variable. Yeah, for example, y equals to beta 1 plus beta 2 x2. uh, Say that we are analyzing a simple regression. Yeah, so this is called a model. Yeah, this is called a model. So sometimes the autocorrelation is present because we are using an incorrect model. So either some important variables are not included or that the model has the wrong functional form. Perhaps it happened because we failed to include another important variable, say x3, another important variable. Say, for example, we are trying to look into factors that will lead to an increase in our overall GDP or in the GDP of a country. And one of the factors that we include is, say, the foreign direct investment. However, we fail to include other important variable. Yeah. For example, we fail to include the influence of uh, internal or domestic investment. So since we fail to include this important variable x3, the influence of the omitted variable. So this is our omitted variable will be recorded in the error term. Since it is recorded in the error term, that error term may not be random already because it records the influence of these important variables towards our dependent variable. So since our error term is no longer random, it means that our error term may present or may contain some what we call as may contain some trend, and this can be translated into an autocorrelation. So the residual from the incorrect model will exhibit a systematic pattern, yeah, that is contributed by or caused by the omission of an important variable in our model. So another factor that can lead to the autocorrelation is the cobweb phenomenon. Yeah, this is another factor that can contribute to the autocorrelation, the cobweb phenomenon. So the supply of many agricultural commodities reflects the so-called cobweb phenomenon. So cobweb phenomenon can be caused when we include what we call as the lag value of the explanatory variable in our model as indicated in equation 10.3. So here we have an example of a supply reacts to price with a lag of one time period because supply decision take time to implement, and this is called a gestation period. So the disturbance term are not expected to be random, for if the farmers overproduce in year T or at present year, they are likely to underproduce in the future, year T plus 1, leading to a cobweb pattern. And another factor that can lead to autocorrelation is, of course, the data manipulation. So data manipulation happen when we massage the raw data. Yeah, when we massage the raw data, it can lead to autocorrelation issue as well. So an example of massaging raw data is when we what we call as translate quarterly data into different time frequency. So here we have time series regression involving quarterly data. Such data are often derived from the monthly data by simply adding 3 monthly observations and dividing the sum by 3. For example, say that we have a higher frequency data, say monthly data, and we wanted to convert this higher frequency into a lower frequency. Say we wanted to convert the monthly data into quarterly data or yearly data. Usually what we do is to add sum of the observation and then divide it by certain value. For example, say that we wanted to convert the monthly data into quarterly data. What we can do is to add 3 monthly observations and dividing the sum by 3 to get the value of each quarters in the data set. And this is called massaging the data. And that can lead to autocorrelation. So this averaging introduces smoothness. So why does data manipulation can lead to autocorrelation? Because data manipulation introduces smoothness, and this smoothness can itself lend to a systematic pattern in the disturbances and thereby inducing autocorrelation. So this is another graphical presentation of autocorrelation. And when we talked about autocorrelation, we can generally divide them or categorize them into two, where we can have positive autocorrelation as demonstrated in figure 10.2a, or a negative autocorrelation as demonstrated in figure 10.2b. Positive autocorrelation means that there is a positive relation between the disturbance at present time with the disturbance term at the previous time period or lag one period. It means that when the disturbance term at present increase, it leads to a further increase in the disturbance term uh, at what we call at the next period of time. So this is called positive autocorrelation. Remember, positive autocorrelation means that when the error term at time t increase, it will then lead to an increase in the error term at time t plus 1. For example, when the error term at 2022 increase, it will lead to an increase in the error term at 2023. Yeah. So when we graphically present as as we can see in figure 10.2a here, we can see that there is a positive relationship between the two disturbance term. So here we have the disturbance term at the present value and the disturbance term at the previous value. So here we have the disturbance term at t minus 1. So if we are referring to the present 2022 present, error term, so the error term at t minus 1 refers to the error term at 2022 minus 1. So it refers to the error term at 2021. So apologies again because we have quite many technical terms, because I believe that that's the most ideal way of, explaining about what autocorrelation is. So we cannot run away from using technical terms. Yeah, but of course I will try to use more general terms whenever possible. So in figure 10.2b, on the other hand, we have a negative autocorrelation. Negative autocorrelation means that the previous when the what we call as when the previous time period error term increase, it will lead to a decrease in the present error term. So meaning that there is an inverse relationship between present error term with the error term at lag 1. So here you can see that there is a what we call as an inverse relationship between present error term with the lag 1 error term. So we can see the positive autocorrelation and negative autocorrelation when we plot a graph of the present error term against the lag 1 error term. Lag 1 error terms mean lag 1 error term means the value of the error term at the previous time period. Yeah. For example, plotting the so here we have plotting the error term at 2022 against the error term at 2021. So okay, before we move to the consequences of autocorrelation, is there any question from the floor? Do you have any questions? Is it all clear? So thank you very much, Kairunisa, Liu, for your response. All right. Then also, you can also give me a thumbs up, yeah, if everything is clear. Okay, so now we move to the consequences of autocorrelation. So before this, we discussed about what is the nature of autocorrelation. Yeah, what are the factors that cause autocorrelation? Now let us look into the consequences of autocorrelation. We will try to see uh, how does autocorrelation influence our estimation. And when we talked about estimation in this, what we call as in this workshop, we are referring to the regression analysis. Yeah, regression analysis, as I said before, this is the most common method used to analyze the relationship between dependent and the independent or explanatory variable for quantitative secondary data. And of course, autocorrelation will lead to several consequences, as you can see on the slide. First is that the autocorrelation will cause the least square estimators uh, to still be linear and unbiased. So meaning that even though our estimation contain autocorrelation, but the least square estimators are still linear and unbiased. Yeah, they are still linear and unbiased. So, however, the estimation are no longer efficient, meaning that the estimation will not produce a minimum variance. So this means that our estimation are no longer blue. So blue stands for best linear unbiased estimator. So even though our model is still linear and unbiased estimator, but it is no longer fast because it is no longer producing minimum variance. Remember, in the estimation, we will always try to ensure that we produce minimum variance. Yeah. However, due to autocorrelation, we may not be able to produce an estimation with the lowest variance possible. So this will lead to what we call as an important consequences in our estimation. Yeah. And of course, as you can see in the slide, the third consequences is that the estimated variance of OLS estimator are biased since the usual formula underestimate the true variance and the standard error, thereby inflating the T values. So a particular coefficient is statistically significantly different from zero. In other words, when our model contains autocorrelation, we will tend to reject the null hypothesis. Or in other words, we tend to conclude that there is a significant relationship between the explanatory variable with the dependent variable. I repeat, due to autocorrelation, we tend to conclude that there is a significant relationship between the dependent and the independent variable. So that is what we call as an important consequence of autocorrelation. Yeah. So of course, apart from that, the usual T statistics or T test and the F test are not generally reliable, meaning that if the T tests are not generally reliable, it means that our conclusion in regards to the significance of the independent variable in explaining the dependent variable is not reliable, meaning that we can question our findings. We can question whether it is truly significant or not. Yeah, the relationship between the dependent and the independent variable. So I will use the term independent variable and explanatory variable interchangeably. So F-test, on the other hand, is used to determine the significance of the model itself. So when the F-test is not generally reliable, it means that our model itself is not generally reliable. In other words, there is something. In other words, we can question our model whether it can truly analyzes the dependent variable or not. So the fifth consequence is that the usual formula to compute the error variance is a bias estimator of the true variance. Yeah, the usual formula to compute the error variance based on our sample is a bias estimator of the true variance. And apart from that, the conventionally computed R square is unreliable. So R square measures the goodness of fit of our model. Goodness of our model. So when the R square increase, that means our model can explain the variance of the dependent variable better. I repeat, if the R square increase or high, it means that our model can what we call as can explain the variance of the dependent variable better. However, if autocorrelation exists in our estimation, that means we can no longer rely on the R square to check the goodness of fit of our model itself. Yeah, so that is a very severe consequence of autocorrelation. And apart from that, conventionally computed variances in standard errors or forecasts may also be inefficient. Yeah, so meaning that the variance in the standard errors of our coefficient or the variance in standard errors of our independent variable may be inefficient as well due to the autocorrelation. So How do we detect autocorrelation? Of course, there are three methods, common methods that we can use to detect autocorrelation. First is the graphical method. Second is the Durbin-Watson method. I think this is the most common method used to detect autocorrelation, and the run test method. Okay, so to discuss about the way to detect autocorrelation, here we have an example. So in example 10.1, we have the relationship between real wages and productivity based on the year 1959 until 2006. So from basic macroeconomics, we would expect that there is a positive relationship, yeah, between real wages and labor. Between real wages and productivity of the labor, meaning that when productivity of the labor increase, it will then lead to an increase in real wages, and vice versa, meaning that when labor productivity decrease, it will also lead to a decline in real wages. Uh, to shed some light on this, we explore the data in table 10.1. So of course, this can only be referred when we looked into the textbook website, which contain data on real wages. However, when we run the analysis, regression analysis between real wages on productivity, we obtain the following results as you can see in equation 10.4. So here we have real wages equals 33.6360 plus 0.6614 times productivity. So 33.6360 is the uh, constant term in our equation. So here we can see that there is a positive relationship between productivity and real wages, where if the productivity increase, it will also lead to an increase in real wages as expected. Yeah. And here we have the coefficient value of the productivity, 0.6614. It means that when productivity increase by a unit, real wages will increase by 0.6614 unit. And of course, apart from that, in the slide, we can also see the information about the standard error of our model, where the standard error of the constant term is 1.4001, and the standard error of the productivity is 0.0156. So apart from that, here we have the t statistics of the constant term and the independent variable. The t-statistics of the constant term is 24.0243, and the t-statistics of the productivity, in this case, is 42.2928. So we can get the t-statistics, yeah, by dividing the coefficient value by the standard error. For example, 33.6360 divided by 1.40001 equals 24.0243, and 0.6614 divided by 0.0156 equals 42.2928. Apart from that, here we have the R square, the what we call as the measure the this coefficient represent the goodness of fit of our model. So here, the goodness of fit of our model, or R square, equals 0.9749. And here we have the Durbin-Watson statistics that is equal to 0.1463. So D refers to the Durbin-Watson statistic that is discussed below. All right. So this is the information about the residual. So we usually or constantly use the term residual and error term. We usually or constantly use the term residual and error term interchangeably. However, residual is referred to the what we call as, it refers to the error term based on sample, while error term refers to the disturbance term at the population. Yeah, so when we draw a model, for example, y, here we have a model, y equal to b1 plus b2 x2 plus mu. So that mu is the residual or error term. And this equation over here, if we're referring to the equation of a population, this is called error term. However, when we are referring this model based on a sample that we collect from the population, we usually refer this term as the residual. However, both residual and error term refers to the disturbance term in the model. Yeah. So whatever factors that can explain why, apart from the constant term and this explanatory variable, will be recorded in the disturbance term. It will be recorded in the disturbance term. And whenever we measure or analyze autocorrelation in the model, we are actually looking into the disturbance term over here. Yeah. And when we talked about the error term of a population, we usually use the symbol mu. However, when we refer about the error term of the sample or the residual, we usually use the symbol E, as you can see here. E at present and E at lag 1. Okay, so here you can see that from 1969 until 2006, we have specific residual. So this is the residual at 1959, down to or until the residual at 2006, if I'm not mistaken. Yeah, 2006. So we have different value of residual at different observation. In this case, our observation is referring to the time series observation. Observation is at 1959, observation at 1960, so on and so forth until the last observation in this data, which refers to the observation at 2006. In the second column, on the other hand, we have the lag 1 residual. For example, here you can see that the lag 1 residual for the observation at 1960 equals negative 5.5315. And this is the same as the residual at 1959. Yeah, so that is why we call them lag 1. We are referring to the value of the residual at the previous time period. So in 1962, on the other hand, the lag value of the residual at 1962 is the same as the present residual at 1960. Sorry, 1961 supposed to be this one, yeah, 61, where it is equals to negative 4.6395. So here we also have at the third column, we have the difference between the present residual minus the lag 1 residual. Yeah. For example, here we have 0.8920. So it equals to negative 4.6395 minus negative 5.5315. And if we square the difference, 0.98920, we can get 0.7958. And at the what we call as at the fifth column over here, we have the residual squared. Yeah, so that residual squared equals to the present value of the residual multiplied by its own value. For example, at 1960, the squared residual equals 21.5250. Perhaps I can enlarge so that you can clearly see. So 21.5 to 60. We obtain that by multiplying the value of the residual at 1960 by itself. So negative 4.6395 multiplied by negative 4.6395 equals 21.5250. And here you can see that the sign is so in the last column, we have the sign of the residual, so they can be negative or they can also be positive because the value of the residual can be negative or positive. Okay, so method number one to detect autocorrelation is by using graphical presentation. And we can obtain that by plotting the residual against time, and this is called time sequence plotting. So this is an example of time sequence plotting based on the examples that we have over here. Yeah, so if we plot this against time, yeah, and graphically present it, this is what we will get. As you can see here, the what we call it, the distribution of our residual against time is not random. There seems to be an apparent trend that we can see when we plot this residual against time. So figure 10.3 shows that the residual do not seem to be randomly distributed. Yeah, they contain some sort of trend. So that trend may implies that we have autocorrelation in our model. So this can be seen vividly by plotting the residual against its lag value, meaning that we plot the first column over here against the second column. Yeah? So here you can clearly see on the horizontal axis, we have the lag one residual, while on the vertical axis of this graph, we have the present residual. So of course, when we plot the uh, present residual against the lag one residual, we can get this what we call as graphical presentation. And based on this, we can suggest that there is a positive autocorrelation between the residual at present with the residual at its lag one. So when this implies that when the residual at lag one increase, it will lead to a further increase in the present the present residual. So method number two, which is I believe the most common way to detect Durbin-Watson, to detect the autocorrelation is through the Durbin-Watson tests. So basically, the Durbin-Watson shows the ratio of the sum of squared differences in successive residual to the RSS, or residual sum of square. And this is the equation to get the Durbin-Watson statistics. Yeah. However, if you're using what we call a statistical software, you don't have to actually estimate the Durbin-Watson statistics manually because it will be automatically what we call as calculated by the software. However, it is good to mention some of the underlying assumptions of the Durbin-Watson statistics. Remember, when we run some econometric analysis, for example, there are some underlying assumptions that we need to know for each of the analysis, including the Durbin-Watson, as you can see here. So what are the assumptions of the Durbin-Watson statistics? First is that the regression model includes an intercept term, meaning that we can only use the Durbin-Watson test when we have added term, when we have intercept term in our model. So this is an econometric model, beta 1 plus beta 2 x2 plus the residual or the additive. Yeah. So We can only use the Durbin-Watson test or refer to the Durbin-Watson test statistics when we include an intercept term or constant term in our model. Second, the explanatory or independent variables are non-stochastic, yeah, meaning that their values are fixed in repeating sampling. So the values needs to be fixed in repeated sampling. The third is that the disturbance term are generated by the following mechanism. So this is how we get the disturbance term by following the equation 10.6, where the disturbance term equals the coefficient of autocorrelation plus plus the residual, yeah, plus its disturbance term. So here we have this rho. This rho here measures the extent of the dependence of the error term, and that rho is called the coefficient of autocorrelation. We are referring to the value of rho to see the extent of the dependence between the residuals. And lastly, the regression does not contain the lag values of the dependent variable, meaning that we cannot rely on Durbin-Watson statistics whenever we have a model, as we can see in equation 10.7, where here we have the lag value of the dependent variable treated as the additional explanatory or additional independent variable. Yeah. In that case, we cannot rely on the Durbin-Watson test, yeah, because the Durbin-Watson test implies that, or one of the assumption of Durbin-Watson test statistic is that the regression does not contain lag values of the dependent variable. So I'm not going to explain about equation 10.8 and 10.9. So we will straight to this, what we call as table over here. So here we can see that the values of the autocorrelation coefficient can either be perfectly negative, it can be between -1 to 1. So the value of the coefficient of autocorrelation, or the rho, is between -1 to 1, where the coefficient of autocorrelation that is equal to -1 implies perfect negative autocorrelation, while the coefficient of autocorrelation that equals to 0 means that there is no autocorrelation in our model, while rho that is equal to 1 implies that our model contains perfect positive correlation. In other words, when our Durbin-Watson statistics is approaching 4, yeah, our Durbin-Watson D statistics, its value can be in between 0 to 4, yeah, where when the Durbin-Watson statistics equals 4, that means our model contains negative correlation, yeah, while if the Durbin-Watson is approaching 0, yeah, it means that our model suffer from positive correlation. While if our Durbin-Watson statistics is approaching 2, that means our model is free from autocorrelation. So how do we refer to the Durbin-Watson statistics? How do we use that to detect whether we have what we call as autocorrelation or not in our model? Well, we have to refer to the two critical values of the Durbin-Watson statistics, namely the lower Durbin-Watson and the upper Durbin-Watson. Yeah, lower limit of the Durbin-Watson statistics and the upper limit of the Durbin-Watson statistics. So, how do we use the Durbin-Watson statistic? Okay, so after we run the OLS regression, we then need to compute the Durbin-Watson statistics. Based on the Durbin-Watson, after we get the Durbin-Watson statistics, as we can see over here, based on this example, the Durbin-Watson statistic equals 0.1463, right? So after that, we need to determine the lower Durbin-Watson or lower limits of Durbin-Watson and the upper limit of Durbin-Watson from the Durbin-Watson tables. So this is, perhaps I can show you an example of the Durbin-Watson table. So this is an example of the Durbin-Watson table. So the Durbin-Watson statistical table can be in different significance level. For example, here we have the 1% significance, and then we also have the 5% significance level. And there are several other informations that you can get from the Durbin-Watson statistical table. So say, for example, based on the examples that we have over here. Yeah. So after we get the Durbin-Watson lower limit and the Durbin-Watson upper limit, then we can make a decision by comparing the Durbin-Watson statistics with the Durbin-Watson lower limit and the Durbin-Watson upper limit. So if, for example, our Durbin-Watson statistics is lower than the Durbin-Watson lower limit, that means there is a positive autocorrelation in our model. Conversely, if the Durbin-Watson is larger, Durbin-Watson statistics is larger than 4 minus lower Durbin-Watson or lower limits of Durbin-Watson, that means we have a negative autocorrelation. And if our Durbin-Watson statistics is between the upper limits of the Durbin-Watson and 4 minus upper limits of the Durbin-Watson, that means our model is free from either positive autocorrelation or negative autocorrelation. So this is the decision rules that we follow to decide or conclude whether our model is free from autocorrelation or not based on the Durbin-Watson tests. All right, so based on the example that we have, our Durbin-Watson statistics equal 0.1463. So here, our time period is between 1959 to 2006. That means our observation equals to 50. So this is an important information that we need to get before we can identify what are the lower Durbin-Watson and upper limit of the Durbin-Watson. We need to check the number of observation, and based on this example, our observation equals to 50 because we have 50 years of data in this particular data set. Of course, to be more precise, 1959 to 2006 equals to 48 years. However, in the Durbin-Watson statistical table, there is no sample size that is equal to 48. The closest one is 45 or 50. You can see the what we call as the sample size on the first column of the Durbin-Watson statistical table, as you can see here. Of course, say that we are referring to the 5% significance level for the Durbin-Watson test. And on the first column, we need to identify the size of the sample or the size of the observation, the number of observation. In this case, the number of observation equals to 50, yeah, because we have 48 years worth of data. Even though, but of course, since in the Durbin-Watson statistical table, there is no observation that is equal to 48, then we need to look into the closest value. In this case, n equal to 50 is the closest to 48. So after we identify the size of the observation or the number of observation, in this case 50, second information that we need to get is the number of regressor. excluding the intercept. So based on the example, our regressor, or the number of explanatory variable that we have, is 1, because we only have one independent variable, in this case productivity. So after we have identified that we only have one regressor, yeah, regressor can be is similar with the term explanatory variable, yeah, even though the regressor can also include the intercept. So here our regressor excluding the intercept equals to 1. So as you can see there, regressor use the symbol k. So k equals to 1, as you can see there. And we also know that the sample size equal to 50. From that, we can see that the Durbin-Watson upper limit equals 1.585, while the Durbin-Watson lower limit equals 1.503. I'm sorry because I cannot point out the on the screen. Yeah, but hopefully you can see where the Durbin-Watson upper limit and lower limit that I'm talking about. Yeah, you can check that value when n equals to 50. The first row equals to 50. Yeah. So 1.503 is the lower limit, while 1.585 is the upper limit. So let me check whether this example is using 5%. Yeah. 1.503 and 1.585. So after we have identified the lower limit and the upper limit of the Durbin-Watson, then we need to compare the lower limit and upper limit of the Durbin-Watson against the Durbin-Watson statistics. Yeah, we need to compare 1.0503 and 1.585 against the Durbin-Watson statistics, in this case 0.1463. So since Durbin-Watson statistics 0.1463 is well below the lower bound, well below 1.503, lower than 1.503, that means if we are following the decision rule as indicated here, yeah, we can simply say, or we can conclude that there is a positive autocorrelation in our model. Yeah, there is a positive autocorrelation in our model. So the lower Durbin-Watson is 1.503. However, our Durbin-Watson statistics is somewhere between this region over here, and its value is 0.1463. That means we have to see that there is a positive autocorrelation in our model. Yeah? So what are the remedial measures then? Well, there are a number of methods that we can use to minimize or reduce the issue of autocorrelation. So we may not be able to solve it entirely, but what we can do is to minimize the problem of autocorrelation. So here we have an example. Here we have equation 10.11. This 10.11 shows the simple regression or simple regression model where we have the dependent variable yt and we have the independent variable xt. B1 is our intercept, while B2 shows the coefficient value of the explanatory variable xt. And of course, here we have ut, which represent the error term or the disturbance term of the model. And assume that the error term follows autoregressive one scheme, yeah, where the present value of the error term is explained by lag one error term. So here we have the present error term, which is explained by the previous value or lag one error term. And of course, here we have the coefficient of autocorrelation that is represented by the symbol rho. And apart from that, in this particular model 10.6, we also have the disturbance term for this particular error term, UT, and it is represented by this VT. And that rho, the value of that rho, the coefficient of autocorrelation is between -1 to 1. To remove the autocorrelation, we can transform equation 10.11 with a 1 period lag, as indicated in equation 10.12. So here we have lag y equals constant term or intercept plus b2xt1. And of course, xt1 here means or represents the lag value of the explanatory variable plus the lag 1 of the residual. And after we have transformed equation 10.11 to 10.12, then we multiply the equation 10.12 by the value of rho on both sides of the equation to obtain equation 10.13. And here we can see that equation 10.13 implies that the rho times lag value of the independent variable equals rho times intercept plus rho times coefficient times or multiplied by the lag 1 explanatory variable plus rho times lag 1 error term. And after we obtain equation 10.13, we subtract equation 10.13 against equation 10.11 to obtain equation 10.14. So this is the equation. Yeah, this is when we subtract equation 10.13 over here against 10.11. Yeah, so y minus rho times y lag 1. And here we have the intercept, and this is the component for the explanatory variable xt. Yeah, we subtract xt against its previous value that is multiplied by rho. And then after that, we have this another error term, vt. So the error term in equation 10.14 satisfies the standard OLS assumption and free from autocorrelation. Yeah, so that equation 10.14 can be rewritten into equation 10.15 as you can see here, where y star x equal to yt minus rho times y t minus 1, while x star equals x t minus rho times x t minus 1, while b star x equals b1 here times 1 minus rho. And this equation 10.15 is called the generalized least square. And this generalized least square solve the issue of autocorrelation in our model. Yeah. Sorry, because of time constraint, I may not be able to explain this GLS entirely. Yeah. So we have to move to the next slide. For this one, I believe that I don't think that I have to explain about this. So this is called the Price-Winston transformation. This is when we what we call as a transform the first observation in our data set. Yeah, because whenever we use the generalized least square, we tend to lose the first observation, and in order to solve that, we use the Price-Winston transformation, yeah, to include the first observation. So at least we have a slightly larger observation, yeah, where we include the first one, the first observation of the dependent and the explanatory variable. And of course, there are various ways to estimate the coefficient of autocorrelation. First is the first difference method. Second is based on the Durbin-Watson-D statistics. I don't think that I have to explain it in details. Third, to estimate the rho based on the OLS of the residuals. And yeah, so though the third, of course, apart from that, there are other various notable methods that we can use to estimate the coefficient of autocorrelation. There are various methods to detect the values of the autocorrelation. Yeah. So among them are the Cochrane-Orcutt two-step methods, Durbin two-step method, Hildreth-Lewis search procedure, and the maximum likelihood or ML procedure. So these are the four methods that we can also use to estimate the coefficient of autocorrelation. So that coefficient of autocorrelation, apart from the Durbin-Watson D statistics, can be used to identify whether our model contain autocorrelation or not. So how do we uh, apart from the generalized least square, what are the other methods that we can use to solve or minimize the issue of autocorrelation? So another method that we can use is called the Newey-West method, or we can also call them as the robust standard error method. And of course, we are not going to look into the mathematics of this test because it is, I believe that it is quite heavy for, or not really that suitable for this workshop. Yeah. However, we can say what we can simply say is that the Newey-West method is a type of analysis that is used to correct the standard error of the model. Remember, this autocorrelation will inflate the standard error, meaning that it will lead to the tendency for us to accept the conclusion that an explanatory variable is significant in explaining the dependent variable. So that is the general consequence of autocorrelation. So if we solve the issue of inflated standard error, it means that we are minimizing the issue of autocorrelation. So how do we deflate, if we can call it deflate, or get the robust standard error that is free from autocorrelation? Well, we can use the Newey-West method. Yeah. So if the standard error is robust, it means that we can use uh, what we call as the results based on the regression to imply or to conclude the relationship between the dependent and the independent variable. So this Newey-West method is also called the HSC. Apart from calling the term robust standard error, we also use the term HAC to represent the Newey-West method. HAC stands for heteroscedasticity and autocorrelation consistent standard error. Yeah, so this HAC does not change the value of the OLS estimator, as it only corrects their standard error. So once their standard errors are corrected, we can then use the robust standard error to conclude whether the independent variable or explanatory variable is significant or not in explaining the dependent variable. So the Newey-West method. So for this particular slide, the Durbin-H statistics, remember the Durbin-Watson-D statistics implies that the model, one of the assumptions of the Durbin-Watson-D statistics is that the model is not autoregressive in nature, meaning that, meaning that the model should not contain the lag value of the dependent variable as one of uh, the independent variables. But in this case, as you can see in equation 10.7, here we have the lag value of the lag value of the dependent variable included as the explanatory variable. Yeah. So here we have its lag value. So when we are having or when we are using this kind of model, that means we can no longer rely on the W-Watson D statistics. So rather than relying on the W-Watson D statistics, we can then use the W-Watson H statistics. Yeah. But I don't think that I have to explain this in details because now it's 10:26 already. But yeah, this is a good information for all of you who are using this kind of model. Yeah. So in this case, remember, you cannot rely on the Durbin-Watson D statistics. So in that case, you have to identify the Durbin-Watson H statistics. How to get the Durbin-Watson H statistics? This is the formula that you're going to use, where H equals rho times square root sample size over 1 minus sample size multiplied by the variance of beta 3. Yeah, the variance as beta 3 or b3 equals the coefficient value of the lag 1 dependent variable in the model. So by using this formula, we can get the H statistics. After we get the H statistics, then we need to uh, differentiate or compare the H statistics against against the critical H values. This H values is obtained based on the student T distribution table. As this is an example of the student T distribution table. This, yeah. So are there any questions? Because I believe this is the last slide for the autocorrelation. Well, now it is 10:30 already, so I'm not really sure whether we have enough time to explain about the another part uh, of of our workshop today. Yeah, where I plan to explain to all of you about the multicollinearity. But what I can do is perhaps to explain about the multicollinearity briefly. Yeah, because I can explain them in details because we only have 30 minutes left. So yeah, before we move to the multicollinearity, is there any question from the floor? I'm sorry again to say that we have quite many technical terms, yeah, for our workshop today. So we have a question from Shan. So can I have your slide for my own study? Yes, of course. Later I'll send this to the committee, to Madam Elizabeth, so that she can share this to all of you who are attending this particular workshop or course. Yeah, don't worry about that. And apart from that, there is actually a more complete explanation, a more detailed explanation about uh, autocorrelation as well as the multiple correlation or multicollinearity uh, that I have done before this. Yeah, during my lecture, and I'll share you the link for the lectures together with this slide as well. Yeah, I'll ask Madam Elizabeth to share it to all of you, that the link to the complete explanation about the autocorrelation as well as the multicollinearity together with the slides. Yeah, don't worry about that. Okay, so if there is no question, perhaps we can take a break for 5 minutes. And then after that, I'll explain to you in brief about what multicollinearity is. Okay, so let us take a break for 5 minutes and we'll be back at 10:35. Okay, shall we continue, guys? Okay, thank you very much. Okay, let's continue. So let's continue our course by discussing uh, the multicollinearity. So just like just like uh, autocorrelation, another important diagnostic test, particularly for regression analysis, is the test for multicollinearity. So there are a number of concepts that we are going to look at. However, due to time constraint, I will try to briefly explain these questions, as you can see on the slide, uh, as much as possible, yeah, before 11 a.m. So perhaps what we can do is to look into the nature of multicollinearity. And apart from that, we will try to identify what are the consequences, both theoretical as well as practical consequences of multicollinearity. And we looked into the methods to detect multicollinearity and what are the what we call as possible solutions to minimize the issue of multicollinearity. So to understand about the nature of multicollinearity, so when we talked about multicollinearity, we have two types of multicollinearity in general. We have perfect multicollinearity and we have the imperfect multicollinearity. And to explain about the nature of these two multicollinearity, here we have in table 8.1, which shows the demand for widgets. And here we have on the first column, we have the quantity or the demand, the amount or quantity of demand for widgets. And in the second row, we have the price of widget. Third row, we have the income per week. And fourth row, we have earnings per week, X4. In table 8.1, we have the data on the demand and its relation to price, X2, and two measures of weekly consumer income, namely the income itself and the earnings. And the income is estimated by a researcher, while the weekly earnings is estimated by a second or another researcher. And in equation 8.1 and 8.2, we have the demand function or the demand model. So in 8.1, we have the demand for widget that is described by a constant term, price, as well as the income per week, while the demand function of 8.2 shows the demand of widget that is described by an intercept, the price of widget, and the earnings per week rather than the income per week. So when we regress equation at point 1, the computer, in this case, refused to estimate. So the computer refused to estimate when we run or when we regress equation 8.1. And to look into that particular problems, we can plot the price x2 against the income per week. And we can get the diagram as you can see here. So when we regress the income on x2, the price of widget, we will get the following results as you can see in equation 8.3, where the income per week is described by a constant term or intercept minus 2 times the price of widget. So this is represented in this graphical presentation as well. So here we have the intercept, and then after that we have the slope of the line, which shows the coefficient value of x2, -2 here, the slope. So this implies, yeah, that the income and price are perfectly linear or perfect multicollinearity. Apart from that, the reason we say that there is a perfect multicollinearity between x3 and x2 is because we can simply look into the what we call as goodness of fit of the model, in this case r squared. Here you can see that the r squared equals to 1. It means that 100% of the variation in x3 is explained by the model, which indicates a perfect multicollinearity between x3 and x2. Yeah, so that is how we say that there is a perfect multicollinearity between the two variables. So conversely, if we substitute equation 8.3 into equation 8.1, so if we include equation 8.3 into equation 8.1, we can get this equation 8.4. Yeah, so in this equation, we have C1 plus C2x2 plus the residual, where C1 equals A1 plus 300A3, while C2 equals A2 minus 2A3. Yeah. So when we regress equation 8.4 instead, yeah, when we regress this equation 8.4, this is the results that we can get, where the demand for widget equals an intercept minus 2.1576 x2. x2 represents the price of widget. So from this, you can see that we lose another variables. Yeah. So this is the consequence. So that variables is the weekly income. This is the consequence of substituting equation 8.3 into equation 8.1. And in cases of perfect linear relationship, we cannot obtain unique estimates of all parameters and draw any statistical inference about them from a given sample. So this is the consequence of a perfect linear relationship. We cannot obtain unique estimates of all parameters and draw any statistical inference about them from a given sample. There is another type of multicollinearity, as I said before this, which is the imperfect multicollinearity. And this is shown based on the model 8.2, where we regress the demand for widget against price and the earnings of what we call as of the consumers or of our respondents. So here we have equation 8.8, where the demand for widget equals an intercept, in this case 148.32, the price of widget negative 2.7975, and the earnings per week in this case equals negative 0.2191. Of course, after that, apart from that, here we have the standard errors and the t-statistics of the estimate. And we also have the goodness of fit of our model, or R square here equals 0.9778. So even though we cannot regress 8.1 because of perfect multicollinearity, we can estimate 8.2. And if we compare the coefficient value of price for both 8.1 and 8.2, the coefficient value here equals to negative. They are both negative, which means that when the price the price of widget falls, then the demand will increase. Conversely, when the price of widget increase, then or more expensive, that means the demand for widget will fall. So that explains, that explains the negative relationship of the price or X2 with the demand of widget represented by Y. So the R value in equation 8.7 with one explanatory variable is also lower, where the R value is 0.9757, whereas as you can see here, the goodness of fit of the model in equation 8.8 is slightly higher with 0.9778. One of the reason why the model, as you can see in equation 8.8, contains a slightly higher coefficient of uh, goodness of fit is because we have an additional explanatory variable, in this case X4, or the earnings per week. So the earnings, as you can see, is statistically insignificant. However, and it is also had the wrong sign. Here you can see that based on this estimation, when the income per week increase, it will lead to a fall in the demand for widget and earnings. And of course, when the earnings decrease, it will lead to an increase in the demand for the widget. So this implies an inverse relationship between the two, between X4 and Y. And this is not as expected because we supposed to expect that when our earning increase, then the demand will increase as well, just like when we wanted the demand for something. Our demand will increase if our income or earnings in this case increase. So that is a positive relationship. But in this case, it is in an inverse relationship where when our income increase or earning increase, then our demand on that particular product decrease. So there is something wrong with the estimation. And if we dig further, if we test the hypothesis that B2, in this case, negative 0.279279775, if we test the hypothesis that B2 equals B3 equals to 0, the hypothesis could be rejected easily, meaning that if we investigate whether B2 equals to B3 equals to 0, the hypothesis could be rejected easily, meaning that X2 and X4 are not supposed to be 0. It means they contain some value, meaning that the model is supposed to be significant in explaining our dependent variable y. But why is it that we have an incorrect sign over here for X4 or our earnings? It implies that there is something wrong with our model. And if we look into it in a more detailed manner by plotting X2 against X4, we can see that there is a high degree of dependency. Yeah, we will get this scatter plot, and when we draw a line for X4 against X2, we can get a straight inverse line, which indicates that there is a high degree of dependency between X4 and X2, meaning that when X2 increase, X4 will fall. Conversely, when X2 decrease, or price in this case, based on our example, then X4 or our earnings will increase. So meaning that they will have an inverse relationship. When X2 increase, X4 will fall. When X2 fall, X4 will increase. So a high degree of dependency between the two. That high degree of dependency means that there is some sort of multicollinearity between our independent variable, and that is what multicollinearity is. High degree of dependency between the independent variable in our model. So that is what multicollinearity, or to be more precise, that is what imperfect multicollinearity is, a high degree of dependency. If we are referring to the perfect multicollinearity, it means that there is a perfect dependency between the two variables in our model. So we can clearly see the high degree of dependency by regressing x4 on x2, as you can see in equation 8.9 over here. And you can simply refer to the goodness of fit of our model. Here you can see that the goodness of fit is rather high. It is 0.9770. It is not equal to 1 because it is not a perfect multicollinearity. But as you can see here, that r square is approaching 1, where the exact value of our r square here equals 97.70, meaning that 97.7% of the variation in X4 is explained by our model. And in our model, we have X2. So 97.7% of the variation in X4 is explained by our model. Is explained including by our price, meaning that X4 depends on X2. The earnings in this case depends on the price. So there is a multicollinearity, imperfect multicollinearity between price and earnings. So price and earnings are highly correlated, and this is the case of near perfect multicollinearity. So what are the theoretical consequences of multicollinearity? So there are several consequences. So of course, in this case, we are simply referring to the imperfect multicollinearity, because remember, if it is a perfect multicollinearity, we cannot obtain unique estimates of all parameters and draw any statistical inference about them from a given sample. Just like when we run the regression, we will not be able to obtain any results. Yeah. But in the case of imperfect or near perfect multicollinearity, then there are several what we call as consequence. So here you can see that so long as the collinearity is not perfect, OLS estimators still remain blue. So this is when we are referring to the linear multiple regression. So our estimate will remain best linear unbiased estimated. However, there are several concerns where the first concern is that the OLS estimators are unbiased, but that unbiasedness is a repeated sampling property. In reality, we rarely replicate the sample. Second, near collinearity does not destroy minimum variance, but it does not mean that the variance of an OLS estimator will be small. Remember, in a regression analysis, we prefer to have the lowest variance possible. Yeah, the lowest variance possible. Third, multicollinearity is a sample phenomenon. It can happen that in any given sample, some or all of the independent variables are highly collinear, that we cannot isolate their individual influence on Y. So this multicollinearity is a sample phenomenon. Even though, for example, in general, one explanatory variable is not associated with the second explanatory variable, but that is the general relationship between the two. However, there is a tendency that based on a sample that we have collected, there is a multicollinearity between the two variables that we include in our model. So that is why multicollinearity is something that we need to identify whenever we run the regression, because it depends on the sample, even though in reality, there may not be a direct relationship between the two variables. For example, say that we include both earning and price. And in general, say that we know that there is no relationship between the two variables in general or based on the population. However, due to some cases or due to some what we call as situation, when we collect some samples, when we collect some samples for both explanatory variables, price and earnings, for example, there may be some relationship between the two based on that specific sample. Yeah, based on that specific sample. So when there is a relationship between the two variable, it implies that there is a multicollinearity in our model if we include both price and earning for that estimation. So this is the practical consequences of multicollinearity. So I will just briefly explain them. First, large variances and standard error of OLS estimators. It then leads to the difficulty to estimate the true value of the estimator and a fall in the precision of the OLS estimator. And second, it will lead to a wider confidence interval. Third, insignificant p-ratios, since the estimated standard errors are high. We will increasingly accept the null hypothesis. So in this case, on the other hand, so remember in when we talked about autocorrelation, we tend to reject the null hypothesis, where it means that we tend to conclude that there is a significant relationship between the explanatory variable and the dependent variable. But in multicollinearity, on the other hand, the consequences or the consequence is inverse, where we tend to accept the null hypothesis. In other words, we tend to conclude that there is an insignificant relationship between the dependent and the independent variable, or between the explanatory and the independent variable. Yeah. So that is the consequence of multicollinearity. Apart from that, we may get a high R square value, but few significant P ratios. Yeah, since we tend to accept the null hypothesis. So in a model which contain multicollinearity, we may have a high R value, meaning that the model has a higher percentage of explaining the dependent variable. However, if we looked into the individual independent variables, these independent variables are usually what we call as insignificant. So there is something wrong in our model in that case. Yet based on the F ratio, these variables may be jointly significant. And apart from that, OLS estimators in their standard errors became very sensitive to small changes in the data and unstable. And wrong signs for regression coefficient, as you can see, based on our example before this, and the difficulty in assessing the individual contributions of explanatory variable to the R square. Because since there is a collinearity between these independent variables, we may not be able to identify which one of these independent variables are the main contributors to the R square, the goodness of fit of our model. So how do we detect multicollinearity? Well, there are several tips that we can follow. Remember, multicollinearity is a sample specific, and multicollinearity is a question of degree. We may always have multicollinearity in our model. It's just a question of the degree, whether it is a perfect collinearity, near perfect, or low in terms of collinearity. Yeah, and it is a feature of the sample and not the population. As I said before this, even though in general or based on the population, X2 and X4 aren't supposed to be related, but when we collect the sample based on certain time periods, for example, or based on certain cross-sectional value or data, there is a relationship between the two, between that time period, for example, from 2000 until 2010, even though based on the population, if we take into account the entire time period, X2 and X4 aren't supposed to be related. Yeah, so that is why we say that multicollinearity is a sample specific. So how do we detect the multicollinearity? Well, there are some tips that we can see or that we can follow. First is that multicollinearity may happen when we have R square in the model. R square means our R square is approaching 1. Remember, our R square is between 0 to 1. When our R square is approaching 1, that means we have a higher R square. Say, for example, our R square is negative, our R square cannot be negative in value. Say that our R square equals 0.9000. That means 90% of the variation in Y is explained by the model. 90% of the variation in Y is explained by the model. So that is a good R square. Conversely, if our R square is, say, for example, 0.2717, that means only 27.17% of our variation in Y is explained by our model. That means that model failed to explain a lot about or a majority of the variation in Y. So when multicollinearity happens, we have a higher R square or high R square value, but few significant key ratios, few significant independent variables. So this explains why we have multicollinearity. Second, we have high pairwise correlation among explanatory variable, meaning that when we run a correlation test between the explanatory variable, for example, x2 and x4, when we try to identify their correlation, that correlation is high. The correlation value is high, and here, high means that the coefficient or correlation value is 0.8, if not higher. Third is that the examination of partial correlation to look into the correlation between two variables by holding the influence of other x variables as constant. We can also check whether our model contains multicollinearity by examining the partial correlation. So meaning that we run the x4, for example, against x2. Beta 1 plus beta 2x2 plus residual. So that is what we call as partial correlation by holding other variable as constant. Or number 4, we can run a auxiliary regression. Auxiliary regression means that, say, we have 3 independent variables. So we run one of the independent variable as the independent variable, say x2, against, say, x4, against the other independent variables. So here we have beta 1 plus beta 2x2 plus beta 3x3 plus residual. So this is auxiliary regression. So if the coefficient value is significant and high, that means x2 and x3 are significant in explaining the x4, which means that we have a problems of multicollinearity. So these are the 4 indicators of multicollinearity. So the fifth, I think the most popular approach is to look into the variance inflation factor. So this variance inflation factor shows how much of the variance of the coefficient estimate is being inflated by the multicollinearity. Yeah, how much of the variance of the coefficient estimate is being inflated by the multicollinearity. So the rule of thumb is uh, a problem exists when any variance inflation factor exceeds 10. Yeah. So if our VIF exceeds 30, it usually indicates a severe multicollinearity problems. And this is the formula to get the VIF of our model. So what is multicollinearity necessarily bad? Well, it depends on the purpose of the study. If the model is used to predict or forecast the future mean value of the dependent variable to estimate the group of coefficient, collinearity may not be bad. However, if the objective is to estimate the individual parameters, then the collinearity may be bad. So what are the possible remedial measures of multicollinearity? Well, there are several remedial measures. However, these remedial measures may lead to several more severe consequences. First is that we may drop a variable from the model. However, if we drop a variable from the model, it may be worse than the disease. Yeah, because dropping the variable may lead to a model specification error. Yeah, so what we can do on the other hand, rather than dropping a variable, what we can do is to add more data or to use new sample. Yeah, we increase the data set in terms of its size, or we use a different sample. Yeah, and another possible remedy is to rethink the model. Yeah, is to rethink the model. Perhaps we have excluded or omitted some important variable in our model. So that can also lead to the problems of multicollinearity. And another, what we call as a remedial measure, is to use prior information about some parameters. So this is as indicated in equation 8.20. So I'll just explain this or show this briefly. And another possible remedy is to transform the variable entirely. Yeah. So here we transform equation 8.21 into equation 8.22 by dividing the left-hand side with the right-hand side of the equation with one of the uh, independent variable that is correlated. In this case, we divide both by x3. Yeah. So just like the autocorrelation, there is also a more complete explanation about multicollinearity that I've done before. So I will share the link for that complete explanation together with this slide to Madam Elizabeth, so that she can share it to all of you. Yeah, because I believe that we have to end our discussion workshop, of course, today, yeah, because we have exceeded the time given. So before we end our what we call as our session today, is there any question from the floor? Is it all clear? Is there any question? So thank you, Karunisa and Ong Yitat, for giving me a thumbs up. Okay, so if there is no other question, I believe that's all for our discussion today or our session today. As I said before this, there are various tests, diagnostic tests that we can use, yeah, to check whether our estimation is following certain assumption or not. Here we are checking whether our estimation, or to be more precise, our regression follows the assumptions of a model that is free from autocorrelation and multicollinearity. Yeah, so there are various tests that we can use to detect both autocorrelation and multicollinearity, and there are also various, what we call as, there are various remedy that we can use to to reduce the issue of both autocorrelation and multicollinearity. Remember, there are several possible consequences when our model contain the two issues, and it is very important for us to address them, especially when we are conducting a uh, secondary what we call as quantitative data, or to be more precise, especially if we are running a regression analysis to check the relationship between the dependent and the independent variables. So later on when you run the analysis for your research, for example, these are among the what we call as these are among the factor or thing that all of you need to address. Yeah, because if you fail to address these issues, then perhaps there are some what we call as there are some there are possible consequences of it. Okay, one of the consequences that people may question whether your analysis can be accepted or not. So that is why it is very important for you to address them. Yeah. So as I said before this, I have a more complete explanation about these two problems or these two diagnostic tests. Later, I will share it. I will give it to Madam Elizabeth so she can share it to all of you. And Madam Elizabeth, do we have other things to do before we end our session?
Ambil gambar, Dokter.
Oh, ambil gambar. So is there any attendance link that the student need to look into? To log into?
No
Huh?
need. No need.
All right. Okay. All right. So just a photograph session, yeah?
Ya, betul, Dokter.
A group photo session. Okay. So I invite all of you to switch on your camera so that we can get a photo together. Thank you very much again for joining our session. Yeah, I hope that you all understand the concepts that we have discussed just now. But if you have additional questions in regards to the diagnostic test, so you can simply email me. Yeah.
Dokter, boleh unshare slide dulu.
Oh, okay. Sorry for that.
It's
Let
okay.
me unshare it first.
Okay, smile. 1, 2, smile. Okay, freestyle. 1, 2. Oh, okay, thank you, everyone.
Okay, thank you very much, Madam Elizabeth. Thank you very much, everyone. So I'll share the slides to Madam Elizabeth shortly. Yeah, thank you very much for joining the session and stay safe.
Okay, thank you, Dokter. Selamat Hari Raya, Dokter.
Thank you. Happy holidays.
Thank you, Dr. Saizal. Selamat
Thank
Hari
you,
Raya.
Ben. Yeah, Selamat Hari Raya too.